Okay guys, welcome to our channel Code with Sunny, and in this video I will be talking about the problem matchsticks to square. Index is 473 and problem is one of the medium type problems of the lead code. Okay, so let me give it a like over here because this problem has explained me, or you can also say taught me a very new good concepts that I'm going to deliver to you now. How to optimize your code, how to make your code have a good runtime, and what are the sequence of steps that you need to follow for the good optimization technique to make your code much more readable, as well as it will run very faster. Okay, so moving further to this problem. Okay, so we have been given an integer array matchsticks where matchsticks of I is going to denote the length of the ith matchstick. That is, we will be given a sequence of arrays, you can see, and every number is going to denote the length of a particular matchstick. You want to use all the matchsticks to make one square, right? And you should not break any stick. Okay, though one things that you need to focus over that, we are going to use all the matchsticks, right? And that is, you cannot left one matchstick and check it out if there exists something that is favoring our answer. You are not going to do that. We are going to use all our matchsticks, and to make one square, this is also important. We have to make exactly one square, and we should not break any stick to make it suitable to forming a square, right? So all the sticks should be taken that is as it is, but you can link them up, and each matchstick must be used exactly one time. Okay, so if a particular matchstick has been used, we are not going to reuse it. Okay, so return true if we can make this square, otherwise false. That is, following this sequence of conditions, if we can make a square, we are going to return true, otherwise we are going to return false. Okay, so I'm also going to discuss the example, right? So for now, let's look over the constraints and whether it is going to help us or not, and what does this constraint is going to convey to us, right? So matchsticks is length is like 15. Okay, so can this help us, whenever the constraints are going to be very small, like n, here the length of the array is like only 15. Okay, so one thing that I want to suggest to you guys, that whenever you will find some length exactly equal to very smaller value, like around 10, 15, or in worst case like 20 or 20, we are not going to say, like 16, 17, 18, or all of that, then you must think of a recursive approach of your solution, or the backtracking approach. Backtracking for like n is around 8 or 10. Okay, like recursive approach, backtracking, you are going to think for these of the approaches when n is going to be like very small. Okay, and when n is like around 1000 or 10 power 5, you're not going to think like of recursive approach and traverse all the possible cases and check it out. Okay, so here n is very small, we are going to use a recursive approach. Okay, one doubt that arises in your mind, how this recursion is going to help us to solve this problem. Okay, the same doubt arises in my mind also when I was solving this problem, and I have got some suitable opinion, suitable thinking. When I have brooded over my mind over this question, then I have got the logical answer also. I'm going to share all of these to you guys. For now, let's move further to understand this problem in a little bit detail, and we will first look over the example and understand how the answer is coming, and what are the sequence of optimization that we have to do to reach the best solution for this problem. And okay, for now, let's move further. Okay, so first let's understand how the answer is coming. Suppose we have some array, right? And we have the sequence of elements like 1, 2, 2, and it's again 1 and again 2. These are the 5 elements of the array, and we need to find a square such that we are not going to break any matchstick. Okay, so let me remove this one. We are not going to break any matchstick. Also, we are not going to reuse any matchstick. So there are two conditions, right? So how we can build any square where every side length is exactly same? It is like build a length 2 over here, and again build a length 2 over here, and again build a length 2 over here. And now we are going to use two things, right? Build a length 1 over here, and then again join it with another one. Again build a length of 1 over here. That is, you can see there are two ones. We are going to use each one exactly one time. That is this one, then all the remaining twos. Okay, so you cannot break any matchstick, like you are going to break this two into two once, and you are going to use that. Also, reusing any matchstick is not possible. Okay, so this is the basically example or explanation of this problem. Okay, so let's move further to understand how we can move further or build up the idea to solve this problem in the best efficient way. Okay, so first I am going to discuss what are the base cases. base cases that you need to consider, or you can also say that you need to take care. Okay, these are the common conditions that when you start solving this problem, you must have been thinking these base cases. And what are these base cases? Suppose we have been given some array of matchsticks, and this is actually the sum. Okay, so this is actually the sum of all the matchsticks, right? Suppose you have to build some square. Okay, now suppose S is the sum of one of the side, and S is again the sum of another side, because since it is a square, all the sides are same. Now 4S must be equal to this sum, right? So when you check it out, if okay, so if sum is not being divisible by 4, or if sum is not a multiple of 4, you can't get the answer, right? So for a given matchsticks, array of matchsticks, first thing you have to check it out. For building a square where every side length is going to be exactly same, the one of the first thing that you are going to check it, and what is that? The sum of the all matchsticks must be a multiple of 4. Okay, so then only you can proceed, otherwise you can't be proceeded. Okay, so this is one of the best cases. I'm going to write down here, like this sum must be modulus 4 must be exactly equal to 0. Okay, now another thing that I need to write it about, what about, okay, so when this condition passes, like sum is now a multiple of 4, then you need to check more conditions. And what are these conditions? Now let's say we are going to denote T as our target, and target is now sum by 4. And we need to build a square where every side length has the value exactly equal to T, right? So I'm going to build a square where every side length is exactly equal to this T value. Okay, now you have to think upon that. What about the case when any matchstick length, let's say mi, when any mi is going to be like strictly greater than the value of t? This is going to be like really very important. Like when any of the matchstick length is going to be like greater than, strictly greater than the target that we want to achieve, that is the square that we want to achieve. If any of the length is going to have the side length exactly greater than the target value, we cannot get that. That is, we cannot build up any square with the given series of matchsticks, right? So we need to ensure that any of the length, that is all of the length, sorry, all of the matchstick length must be what? At most the value of t, right? So I'm going to write down one condition, another, that is the next condition. Okay, so I'm going to all mi matchstick length must be at most this t value. Okay, now if this condition passes and also this condition passes, then only I can move further. Okay, and what are the more conditions? Okay, just tell me one thing that we, okay, so I'm just writing down one thing. We are going to use recursion. Okay, and what is the basic idea of recursion? That is, you have to include this any of the matchstick into your answer, and consider this as that including this matchstick can be like can give us the correct answer, or we cannot get, that is, we cannot fetch the correct answer also. There are two possibilities. Including a particular matchstick mi can give us the can give us the correct answer, like we can get a valid square, or does not including this mi, that is, if we are not going to include this mi at a particular side length, what about the next one? We need to check all the possible cases, right? If you're not going to understand this right now, no need to worry about. I'm going to explain this recursive step in a little bit detail in just a few moments later. Okay, so for now you need to ensure one thing also. And what is that one thing? Okay, so let me write down clearly that this is my third optimization, or you can say third base case. Now what is that base case? Sort all the mi values in what? Non-increasing order. And what is the reason behind that, right? When we are going to just use a particular matchstick to a particular, that is when we are going to include a particular matchstick, that let's say a matchstick value 5. Okay, so let me write down it clearly. Okay, so this is order. Now when we include some particular matchstick 5, and then we include some particular matchstick again 5, and there are a lot of matchstick, right? Okay, so we have some sequence of matchstick like 5, 6, 7, or some values of 5, and suppose there exists some another matchstick whose value is like 10 power 9. Okay, and these two conditions are like satisfied. Then only I'm going to talk about this third condition, right? So suppose we have some sequence of matchstick having the value length exactly very smaller, like 5, 6, 7, and there exists another matchstick whose length is like very big, like 10 power 9, and these two conditions are already satisfied. Okay, then what is the best case to improve your runtime, right? If you are not going to use this statement, I guess you are fine, you may get TLE, but for better case, for improve your runtime, you need to sort the matchstick in non-increasing order. Okay, so suppose we have some matchstick whose length is like very big, and you need to build up a side whose length exactly equal to the target. Then the best case scenario is to always pick up the maximum length of this matchstick first. That is, when you are going to include the maximum length of matchstick, then the probability of getting your answer increases as fast as possible. The recursive step becomes concise, and concise means the number of recursion calls becomes very less if you use this condition. That is, first process the higher value of matchstick lengths, then we are going to move further to the smaller values. Suppose you are going to use the first smaller values, then it will take a lot of time, because the bigger values are coming at the last step of the recursive calls. Okay, then the processing takes much time. That is, the recursive calls take much time. So these are the three steps you are going to do. Okay, this is basically a checking step, this is also a checking step, but this is like a good optimization step. And you are going to do this. Why you are going to do this? You are going to do this for improving your runtime. Improve runtime. Okay, now moving further to the recursion steps, how we are going to build up the recursive things, and what will be the sequence of codes. Let's move further to understand this. Okay, so we are now at a state where all these conditions are like satisfied. That is first two checking condition, last one also. Now moving further to the recursion step, what I have done is like maintain four size vector. Initially, I have not maintained the four size vector. I have used the variables, but to make your code readable and concise, I am going to use a four size vector, and this is going to basically denote the sides of square. Like we have some square, and this is the first side, and this is second side, this is the third side, and this is the fourth side, and the array is also going to denote the something. This will store the all the sides, like this first side, what are the length of the sides, that is the total current length of this side 1, and current length of this side 2, current length of this side 3, and the so on, right? Okay, and also we have some matchsticks, right? We have some n length size array, and this is going to denote the size of the matrix. And note that this array is sorted in non-increasing order, right? So I'm also going to write this thing. This is already sorted in non-increasing order. Now what I'm going to do in recursion step, call the recursive function passing the parameters, like passing the initial position of the matrix that is being operated, right? So suppose we have some sequence of matrix like 5, 6. Okay, the array is sorted right now. So 4, 3, 3, and 2. Suppose I am just initially passing this one 5, then it will work upon this 5, and how it will start working upon, like okay, so this is 5 1. So what I'm going to do is include this 5 into this, that is 4. There are 4 sides right now, no? Side 1, side 2, side 3, and side 4. Okay, so include this value of 5 into this first position of this array. Note that this is going to denote the sides of square, and then recurs for the next position, like because if this 5 is satisfied over here, and what is the checking condition? That is, whenever you start including one of the matchsticks, that is let's say this position is like s of I, and this is the S vector whose size is 4. You need to ensure one thing, right? Whenever you want to include any matchstick of a particular length, you need to check one condition, S of I, that is the current side length that it is holding, plus the value that you are including into your current side, and the value is 5. 5 must be what, less than equal to this target T, and this is important, and this is T is actually sum by 4, and we need to notice one thing, that we want exactly the value of T for every side length, right? So you need to ensure that this condition holds, otherwise you cannot proceed. Suppose this condition holds, then what you are going to do, since it is a recursive step, you will increment your this pointer, that is the pointer pointing at 5, to the next step 4. Okay, and when you are at this one, again you are in another recursive function, where you need to check whether including 4 to this 5 is satisfiable or not, right? So you want to check again. Now my current this is again a 4 size vector. Now in again another function, what you are going to do is include 4 to this position. Now initially it contains the value 5, plus you want to include 4 now, and if this is less than t, yes, this should be included into your answer. Suppose this condition fails. Okay, when this condition fails, then the pointer, and which pointer I'm talking about, this pointer, like I've already tried to put this 4 at this position. Okay, so we cannot put this, then I will try to put this 4 to this position. Okay, when I am able to put this 4 to this position, like this condition satisfies, okay, then I will move to the next position, that is increment this position to this position. Okay, then I will try to put 3 to back to this position. If I can, then I will move my this pointer to the next one. Otherwise, if I cannot be able to put 3 to this position, I will try to put my 3 to this position. And if I can, then I will increment this position to this next one. Otherwise, then I will try to put my 3 back to this position, and so on. This is actually basically the recursion step. Whenever you are trying to put a matchstick to a particular side, that is include that value to a particular side, and if that happens, it does not claims that you cannot put a side, then you can just increment your current side's length value that it is holding, and if it cannot put the side, then you have to just check for the next side that you want to include, right? So basically, this is actually easy one. Writing the recursive thing easy, but the main thing of this question is that how you are going to optimize your code, right? You can do the recursive step. Even I can also do. You can also do. But checking these 4 conditions, although I have left one optimization that improves your runtime, I am going to talk about that optimization while discussing the code. Okay, so for now, let's move further to the coding part and let's understand how the sequence of operation is going to happen and how I am going to write my code and efficient code. Okay, so let's move further. Okay, so you can see there are a lot of like TLEs, 3 TLEs, because I'm not able to initially figure it out the like correct solution with the optimization. Then I've got some accepted technique by this one is like I've got accepted by sorting the values, matchstick values in non-increasing order, right? You need to do that. Then I've got accepted, but the runtime was very bad. Then again some optimization. Then I've got this one. Then finally I've got the good code like of 36 ms. Okay, and this is what the secret optimization, dynamic programming optimization that I have to do. Okay, so let me discuss this one directly, right? Okay, so I've also commented it for the readability of this code, right? Okay, so this thing, this already happened. I will also discuss it about. For now, let us move on to this actual main function, make a square, right? So I will, it will take a parameter of sticks, right? And first I will find out sum, that is sum of all matchsticks length, and I am doing this with the help of accumulate function of STL. Then I will sort in non-increasing order, and the reason is it decreases the runtime as well as reduces the chance of that is the chance of TLE, since bigger sticks are going to be processed at first. This is going to be like really very important to improve your runtime as well as to reduce the chance of this TLE condition. Sort sticks in non-increasing order, and this sides is going to maintain the what is the current side length of every side. There are 4 types of sides of the square, and every length must be same, and this is going to show what is the current state of the lengths of sides that are being included to our answer. Okay, you can see previously what I have been doing here is like not maintaining the sides vector, as just taking the parameter of side 1, side 2, side 3 and side 4 also. You can also do like that, but taking this one is like a good one for improving your readability of the code, right? Now I have to check the condition. If sum is not a multiple of 4, or stick's length, that is the given vector, must be at least 4, and if it is not, that is any of the condition holds true, we are going to return false, denoting that we cannot build a square of side 4 whose length is same. Now sum is now our target length, and length, that is the length of each side. So I will divide it by 4. Now check it out. If any of the sticks has the length exact is to more than the target side length that we want to achieve, then I'm going to return false also. And this can be easily done by checking the first value of this array being sorted in non-increasing order already, right? So sticks of 0 is greater than sum, strictly greater than sum, return false. Otherwise, do the recursive step. Okay, now the comes the main thing, recursive step. So I will check it out, the base condition of this recursion, that is every side is exactly equal and it is matching with the target value. And what is the target? Note that the target is actually sum by 4. Sum is the sum of the matchstick's length. Now this, if this happens, then return true, otherwise return false. Okay, now you note that this is the AND condition that I mentioned in between these two, these four conditions, right? So start iterating 4 times and check it out for a particular site if my current position of matchstick, that is the current matchsticks, can be included in sites of I. If it can be included, and how we are going to check that? Check whether on adding my current matchstick length increases the target or not. Not I'm not writing that increases the target. It is like on adding my current matchstick to a current side that is holding my current sum of the sides that has been already included. If on adding my current matchstick length to this one is has the new value exactly strictly greater than the target value, we cannot move further. That is, this matchstick cannot be included into that side length. Okay, that that side which is holding the sum, right? Or this condition happens, already happened. Okay, so this is going to be like really important. I'm going to discuss in a minute. For now I will move further to this one. Okay, or that is, if my on including my current mastic length to my current side that is holding the sum is strictly greater than the target new value, or this condition holds true, continue means that I'm not going to use this matchstick to put into my current side sum. Otherwise, increment your sides of I by current matchstick length and recurs for the further subsequent matchsticks. And if it comes true, if it returns true this recursion, you are going to also return true that yes, there exists some valid square. Otherwise, you need to decrement this sides of I also. Okay, and if all the condition holds and we are not going to fetch some return as true, we are going to return as false, right? This is basically the recursion step. Now comes the main thing. What is this already happened sites and I? Okay, so this is like when you look over this DP optimization, you can see I'm passing my current position I, that is the current side number and the sites vector. And what I'm checking is for all these sites which are strictly less than this my current position, you can see I less than pose. And if there exists some side some side sum whose sum exactly matches with my current sum, that is sides of I exactly matches with sides of pose, I am going to return true that this condition is going to be true, so I'm not going to move further. Okay, so this is basically a condition that avoids the repetitive recursive calls. And what is that repetitive recursive calls? Let us try to understand that. Suppose we have some 5379. We have some certain state of sides, that is the sum of the first sum, that is the side 1 is going to hold this sum, side 2 is going to hold this sum, side 3 is going to hold this sum, and side 4 is going to hold this sum. Okay, so I have done something wrong. Okay, so I'm going to use again 5 over here. 5359. Okay, suppose my current matchstick length is 6 and I need to check it out if on adding 6 to any of these positions whether we can add this or not, right? So suppose I'm trying to add this to first position, that is first side, 5 plus 3, then my new vector is 5 plus 3, 3, 5 and 9, right? This is my current one. And suppose if I'm adding to second position right now to 3 plus 6, and it is 5 and it is 9. Okay, so you must be take care that I have done some mistake. You have to do like 5 plus 6. Okay, 5 plus 6, 3, 5, 9. 5, 3 plus 6, 5. That is, I am adding 6 to this first one. Then I am trying to add this 6 to second one. And then I am trying to add this 6 to 5 one, and so on. Okay, okay. Then when you try to add 6 to this third position, you need to take care for that one thing. That is 5, 3, and when you add this to 5 plus 6 and then it comes over 9, you can see that there is a state that I'm going to I'm going to call another recursive call for this condition, and this recursive call is going to exactly match with this recursive call. Why? You can see there are two parameters same, like 5, 3, and again 5 plus 6, 5, 3, again 5 plus 6, and then it is 9. Okay, so it means that we are again calling our recursion with the same value of parameters. and it is not going to be useful. And how it is not going to be useful? Suppose this step, when you put 6 to this step, and when you call a recursive, that is when you recurse for the next of the position, suppose this step, on adding 6 to this step, return false. Okay, on adding 6 to this step, it returns false. Then it is obvious that when you add 6 to this step, it will also return false, because the state of the parameters of the sites are really same. So it is not going to be useful to move to this step, right? So this is the optimization. So I'm going to check it out whether there exists some value which is already matching with my current value right now. Okay, so this is what already happened. Function is going to check it out. Okay, and you can see that how it improves the runtime from 1804 to 36 ms, and it is wonderful, right? So the recursive step is this, and already deep happened function is this, which is actually the DP optimization. Okay, so if you have any doubts, I will recommend to mention in the comment section of the video, so that we are aware about that you are getting these doubts, and we will help you guys to move further with these doubts and to get it cleared. Okay, so I will ask the viewers to like this video, share this video, and to subscribe to YouTube channel for latest updates. Thank you for watching this video.